Hello, everyone. I hope everyone can hear me. Welcome to the PAPERI webinar series. I'm Dr. Selma Kabashi. I will be today's moderator. Thank you for joining us for our session on interethnic differences in cancer risk and survivor, integrating epidemiologic, clinical, and multi-omic data. I'm delighted to introduce our esteemed speaker, Dr. Brian Huang. Dr. Brian Huang is a cancer epidemiologist and an assistant professor in the Department of Population and Public Health Sciences at the Keck School of Medicine of USC. His research focuses on the etiologic, mechanism, and racial and ethnic disparities of pancreatic, colorectal, and lung cancer. Dr. Huang's work integrates epidemiologic, clinical, and multi-omic data from racially and ethnically diverse populations to investigate interethnic differences in the risk and survival of cancer. In today's talk, Dr. Huang will share his research in the multi-ethnic cohort on gene-lifestyle interaction of polygenic and lifestyle risk scores on colorectal cancer risk and the epigenetics of lifestyle risk factors. Please join me to welcome Dr. Brian Huang. Please note that we will have a live Q&A session at the end of the webinar, so you can use the Ask a Question feature to submit your questions. Please mute your microphone. Session will be recorded and will be available on our YouTube channel. Dr. Brian, the floor is yours.
Great, thank you so much. Can everyone hear me? Good. Appreciate the introduction and thank you for inviting me here today. Very happy to be here to share my research with you on genetics and epigenetics and risk factors for colorectal cancer risk in the multi-ethnic cohort study. So I'm going to share my slides. Give me 1 second, sorry. Okay, can everyone see this?
Yes, yes, we can see it.
Great, okay.
Please mute your microphones.
Okay, here we go. Cancer is a significant public health issue in the United States. For many cancers, especially the ones that I study, there are known racial and ethnic disparities in both incidence and survival. This graph on the right shows the most recent trends in cancer incidence rates for pancreatic cancer in the United States, where non-Hispanic Black individuals have higher risk, as represented by this line, while non-Hispanic Asians have the lowest risk. In our work, we have also observed that these disparities still exist after adjusting for differences in the distribution of known lifestyle risk factors. Thus, other biologic factors such as omics may further explicate the differences in cancer risk across populations. Studying omics may allow us to identify racial and ethnic specific risk markers or carcinogenic mechanisms. However, as existing studies have been mainly performed in homogeneous samples, more efforts are needed to investigate omics in diverse populations. Therefore, the goals of my research program are to understand cancer disparities by, number one, first investigating how much of this is explained by lifestyle factors, and secondly, by explaining omics factors such as genetics, epigenetics, and metabolomics, and finally, by studying the interaction and pathways between lifestyle factors and these omics factors. In the time that I have with you today, I'd like to share findings from two of my recent studies. The first is a study of the interaction of lifestyle factors and polygenic risk scores on colorectal cancer risk in the multi-ethnic cohort study. And the second is an epigenome-wide association study of smoking dose across 3 prospective cohorts, which was published earlier this year in the American Journal of Human Genetics. Now, first, I'll start with the gene lifestyle interactions in colorectal cancer risk. Colorectal cancer is a significant issue in the United States with known racial and ethnic disparities. This graph is showing statistics from the American Cancer Society that show differences in colorectal cancer incidence on the left and mortality on the right, split up by race and ethnicity and by sex. Using whites as a reference group, as represented by this middle dark green bar, we see that in all sets of plots, Black and American Indian and Alaskan Native individuals have higher rates, while Latino and Asian Pacific Islanders have low rates for both incidence and mortality. One method to reduce the burden and disparities of colorectal cancer is to improve our understanding of its genetic and lifestyle etiologic factors across populations. Previous genome-wide association studies have identified more than 200 single nucleotide polymorphisms, or SNPs, associated with colorectal cancer risk. Recently, a polygenic risk score of 205 SNPs was developed using all risk loci identified from GWAS performed in European and Asian populations. There are also several known lifestyle risk factors for colorectal cancer, including smoking, obesity, alcohol use, and diet, and so on. Given colorectal cancer's multifactorial etiology, understanding the interaction of lifestyle and genetics has the potential to improve risk prediction and to identify high-risk subgroups who would most benefit from targeted prevention. However, past epidemiologic research evaluating the interplay of lifestyle and genetics has been generally limited to homogeneous populations of European ancestry. Thus, racial and ethnic minorities are underrepresented in these gene environment studies of colorectal cancer etiology, despite having a disproportionate burden of colorectal cancer. Therefore, the primary objective of this study was to further elucidate colorectal cancer risk by integrating information from lifestyle risk factors and genetics. And specifically, because past studies were mainly done in white populations, our second goal was to evaluate whether the interaction of lifestyle and genetics varies across races and ethnicities. We performed our study using data from the Multiethnic Cohort study, which is a diverse prospective cohort started here at University of Southern California and the University of Hawaii back in the 1990s. The multi-ethnic cohort, also known as the MEC, is comprised of over 215,000 individuals from Los Angeles and Hawaii from 5 main racial and ethnic groups: African Americans, Native Hawaiians, Japanese Americans, Latinos, and whites. Among this cohort, about 70,000 of them provided a blood specimen, of which we were able to generate genetic data. After exclusions, our analytical sample included about 68,000 individuals with genetic data. The mean age of the sample was around 68 years old, and 54% of the population was female. Across our 5 racial and ethnic groups, Japanese Americans made up of the largest proportion at 33%, followed by Latinos at 24%, whites at 20%, African Americans at 15%, and finally Native Hawaiians at 8%. For our sample, we estimated genetic risk using a polygenic risk score, or PRS, that I mentioned earlier of 205 genetic variants derived from Asian and European GWAS summary statistics. This PRS was calculated using weights from the multi-ancestry meta-analysis and categorized as quintiles and as high versus low levels split by the median value for our analysis. We then calculated a healthy lifestyle score, which was based on the distribution of smoking, BMI, alcohol use, diet quality, which we assessed using the Alternative Healthy Eating Index 2010, and physical activity. For each risk factor, individuals were scored from 0 to 1, with 0 for the unhealthiest level and 1 for the healthiest. For instance, for smoking, never smokers got a value of 1, that was the healthiest factor, and current smokers who smoked more than 20 cigarettes per day got a value of 0. We then summed up all the values with the total score ranging from 0 to 5. Again, 0 being the unhealthiest and 5 being the healthiest. We conducted 4 primary sets of analyses to understand colorectal cancer risk in our population. First, we modeled either the polygenic risk score or the healthy lifestyle score alone. Next, we looked at their interaction by evaluating the impact of the lifestyle score across levels of the polygenic risk score. And finally, we evaluated their joint effects by looking at risk with different combinations of lifestyle and genetic risk. And here our reference group were those with the lowest lifestyle and lowest genetic risk. Because our outcome was incident colorectal cancer, we used Cox regression analysis, which adjusted for demographic factors such as age and sex, race, ethnicity, as well as known colorectal cancer risk factors such as family history, a personal history of colorectal polyps, education, diabetes, NSAID use, and multivitamin use. We also adjusted for principal components in our genetic analyses to adjust for population stratification. In our cohort, we identified about 1,300 incident cases of colorectal cancer over a median follow-up period of 15.1 years, which gave a crude incidence rate of 14 cases per 10,000 person years. This graph here showing the number of cases in our cohort split up by race and ethnicity, and we see that the largest proportion of cases were in the Japanese American population, followed by Latinos and African Americans. In terms of incidence rates, the highest rates were observed in the African American and the Japanese American population, while we had lower rates in Native Hawaiians and whites. The distribution of the polygenic risk score was generally even across race and ethnicity, with slightly elevated values for Japanese Americans and the white participants of the MEC. For the healthy lifestyle score, we found that the average healthy lifestyle score was highest in Japanese Americans, as shown here in pink, and lower among African Americans, Latinos, and the Native Hawaiians. In our modeling, we observed a positive trend between higher levels of the polygenic risk score and risk of colorectal cancer. In the entire cohort, higher quintiles of genetic risk were associated with greater risk. This is a forest plot showing the associations for each increasing quintile of the polygenic risk score, with quintile 1 being our reference group. And you can see we see a nice positive trend with increasing levels of colorectal cancer risk with increasing levels of the PRS. We found that the highest quintile of the PRS was associated with a 2.4 times increased risk of colorectal cancer in the entire cohort. When stratifying by race and ethnicity, we see that the PRS does generally replicate in the 5 racial and ethnic groups. So we have a split by African American, Japanese American, Latinos, Native Hawaiians, and whites here. And in general, we see an increasing trend of increasing risk with increasing PRS levels across all of the 5 racial and ethnic groups. Now remember that the PRS was established using GWAS data on Europeans and Asians. And we see that in our data, the PRS does generally replicate well in the Japanese Americans and the white populations. But we also do see that it does also replicate in the other racial and ethnic groups in the MEC, such as African Americans and the Latino population. We see some larger confidence intervals in the Native Hawaiian group. The trend isn't as nice, but this is likely because of the fact that we have a smaller sample size in the Native Hawaiians. If you notice the number of cases, it's much lower compared to the other racial and ethnic groups. In this analysis, we found that the highest quintile of the PRS increased risk for colorectal cancer, ranging from 1.6 times in Native Hawaiians, all the way to 3.5 times higher risk in Japanese Americans. We then observed the opposite trend for the healthy lifestyle score, where higher levels of the healthy lifestyle score were associated with decreased colorectal cancer risk. Again, these are results for the entire cohort. So we see this nice trend decreasing risk with increasing healthy lifestyle score. The highest quintile of the healthy lifestyle score was associated with a 33% lower risk of colorectal cancer. Again, we then evaluated this by our 5 racial and ethnic groups and observed generally similar trends across the 5 groups. Those in the 5th quintile had a decreased risk for colorectal cancer, ranging from 21% in Latinos to 56% in whites. But in general, we're seeing the similar trends of decreasing risk with increasing healthy lifestyle score. Next, we looked at the interaction between the healthy lifestyle score and the polygenic risk score, which we did by stratifying the cohort into those with low genetic risk and high genetic risk, using the median PRS as the cutoff. When looking at those in the low PRS group, we actually do not see the same decreasing trend or significant findings for the healthy lifestyle score. Notice that the p-value for trend here is non-significant, indicating no dose response of the healthy lifestyle score and colorectal cancer risk. The trend that we saw earlier was actually much more apparent among those in the high PRS group. Here we see that the highest quintile is associated with the most decreased colorectal cancer risk, here at a 45% decreased risk. And in this high PRS group, we do see a significant P trend, indicating a significant dose response with higher levels of the healthy lifestyle score with decreasing levels of colorectal cancer risk. The difference in the association across the low and the high PRS groups were statistically significant, indicating that the healthy lifestyle score had more of an effect among those with higher genetic risk. Again, when stratifying by race and ethnicity, we see similar patterns where the healthy lifestyle score was generally non-significant among those in the low PRS group. Notice that all the confidence intervals here cross the null of 1, and there's no evidence of trend as indicated by these P trends here. The protective trends for the healthy lifestyle score was more evidence in the high PRS group across all racial and ethnic groups, as shown here on the right. Here we see that the protective trend is present in African Americans, Japanese Americans, and whites. The difference in effect across the low and high PRS group was significant in the white participants, where there is generally no association in the low PRS group and a very evident decreasing trend in the high PRS group. For the high PRS group in the white participants, the highest quintile was associated with a 67% decreased risk for in the high polygenic risk group among whites. Next, we evaluated the joint effect of the lifestyle score and the polygenic risk score, where we categorize individuals into 6 categories based on low or high genetic risk, and low, moderate, and high lifestyle risk based on their lifestyle score. In this analysis here, individuals with low genetic risk and low lifestyle risk served as our reference group. And here we observed a very nice trend with increasing colorectal cancer risk, with increasing joint genetic and lifestyle risk. But notice here that even the healthiest individuals in the high genetic risk group, so here, still have higher or similar risk compared to the unhealthiest individuals in the low PRS group. This demonstrated to us that even if you have high genetic risk, having the healthiest lifestyle can only decrease your risk so much compared to those with low genetic risk. When split by race and ethnicity, we again see similar patterns of increasing colorectal cancer risk with increasing joint genetic and lifestyle risk. This was generally present across all the ethnic groups, but again, notice we're having larger confidence intervals for populations such as Native Hawaiians that have smaller samples. But we're seeing the most significant trends in the Japanese Americans, the African Americans, Latinos, and the white populations. But again, the non-significant trend likely is driven by the smaller sample sizes in this group. Lastly, we calculate the cumulative colorectal cancer risk from our observed age span of ages 45 to 85 at different levels of genetic and lifestyle risk. We did this by tabulating the data into live tables stratified by lifestyle risk as low, moderate, high, which I showed earlier, and PRS categories at different percentiles. And here we're looking at 20%, 50%, and 80%. 20% is indicated by the PRS percentiles are indicated by color, 20% at blue, 50% at yellow, and 80% at green. And the line patterns are indicated by lifestyle risk score. A solid line indicates those at the highest lifestyle risk. This dashed line is moderate, and the smaller dashed line is for low lifestyle risk. In this analysis, we observed that those with the highest PRS, so those in the green line, have higher risk of colorectal cancer across the entire observed lifespan, but we're having greater stratification at older ages. At the age of 85, the cumulative risk of colorectal cancer was, among the 80% PRS group, was the highest, ranging from 2.8% for those with low lifestyle risk and 3.5% for those with high lifestyle risk. Another thing that we observed in these plots is the overlap between the low lifestyle risk category and the higher PRS groups and the high lifestyle risk categories in the lower PRS groups. So notice here I've indicated an overlap of the 80% PRS and low lifestyle risk with the 50% PRS in yellow and high lifestyle risk. There's an overlap here. And then another overlap among the 50% PRS in yellow with low lifestyle risk, but the 20% PRS in blue and high lifestyle risk. This indicates that modifying your lifestyle can help bring down your risk to a level that's reflective of someone with lower genetic risk. This led us to ask that given that your genetics cannot change, are there certain ages where the difference in colorectal cancer risk is it greatest among those with high and low lifestyle risk? And this graph here represents the difference in cumulative risk between the high and low lifestyle groups across the ages of 45 to 85, again stratified by the PRS percentiles. And the highlighted regions here indicate ages where this difference between high and low lifestyle risk is statistically significant, which range in general from around age 60 to 80. And here we see that the peak difference between high and low lifestyle risk for all of these PRS percentiles was around the age of 76. In other words, we're showing that this band here from 60 to 80 seems to show that there's a higher difference in risk from high lifestyle and low lifestyle risk. From this multi-ethnic investigation of gene-environment interactions, we found that the PRS and healthy lifestyle scores are useful risk assessment tools, with their joint estimation being the most informative for colorectal cancer risk prediction in our population. Moreover, a healthy lifestyle may offer greater protection among those more genetically susceptible, as we saw that there was a decreasing trend of the healthy lifestyle score among those in the higher PRS group, but no significant association among those in the lower PRS group. Our study showed that incorporating genetic and lifestyle information can help to enhance the risk stratification of colorectal cancer. Importantly, because patterns were generally similar across race and ethnicity, integrating this information has the potential to greatly improve colorectal cancer risk prediction across diverse and understudied populations. I'll stop here to see if there's any questions before I move on to our next study.
Oh, I am checking the. There is no question I'm aware of.
Oh, I see a hand raised from Wafa.
Yes, there's a clap. Yes, Wafa.
Hello.
Wafa, we can hear you.
Thank you very much.
Yes, you can hear me?
Yes.
Yes, I can hear you.
Yes, thank you very much for your presentation. I have a question regarding if the study will help us to develop online calculator or something like this that we see in breast cancer.
Sorry, I didn't catch that. So the question is if it's similar to an
Uh,
online calculator?
yes, online calculator for the risk of colorectal cancer, like we see in breast cancer.
Oh, is there something that's established right now? No, I
Okay.
think there are a number of prediction risk models that they use in the clinic, but I don't think there's one central one, like the Gale risk model for breast cancer. I don't think that's established yet. And definitely
So
not one
what
central one
will
that's
be
incorporating.
okay? So what will be the next step after these findings?
Yeah, the next step, so it's under review right now, and hopefully we can develop a prediction model that integrates all this information. And we can assess that in our 5 cohorts, but hopefully we're able to also validate this in other prospective diverse cohorts to understand the clinical utility of this.
Okay, so the step is validation of the results, is this results.
Correct, yes.
Yeah, okay, thank you.
This specific study was only looking at lifestyle and genetics, but I do have a grant going in to also look at other omics such as epigenetics. So the goal of my research really is to understand other omics risk factors for colorectal cancer, with the ultimate goal of integrating that all together for a multi-omic prediction model.
Okay, thank you, Dr. Brian, for the insightful presentation. I'm checking now if there's any other question. So to any of the audience, yeah, I can see Andrea raising her hand. For the others, they can also type a question into the Q&A box. Andrea, you can unmute and ask. Hello, Andrea. Can you hear me? Any other question? I'm checking the chat now.
But we can always revisit this at the end too.
There's a question in the chat. How was the lifestyle scores calculated?
Oh, I can go back to that slide.
Yeah.
It was calculated using a score of 0 to 1 for these 5 risk factors. So smoking, BMI, alcohol use, diet quality, and physical activity. And we gave them for each risk factor, we gave them a value of 0 to 1 based on which was the unhealthiest level and the healthiest level. I showed the example of smoking, but let's look at BMI. So if you have a normal BMI, you get a value of 1 for healthiest value, and then a value of 0 if you're obese. Then we summed up all these values for all the 5 risk factors, and then we had a total score ranging from 0 to 5.
Hello, Doc. I need a clarification. I'm the one who asked the question. These scores, you define them yourself, or they are internationally accepted scores for these risk factors?
This one I established myself, but we did use guidance from past studies that use scores similar to this.
Okay, thank you.
There's another question in the chat. Was there effect of gender on the outcomes noted?
I did do the analysis split up by men and women. The results are generally similar. The only difference is that the interaction between the lifestyle score and the PRS was only significant in the females.
So what's the implication of this result? Is
Among
there's
the
a
female,
being more significant in emails? If there's an implication there?
For me, I think it's because at least the females in our population are healthier than the males. So it could just be the fact that we have more variation in the females that have shown effect. That is my understanding so far, but because if I look at the patterns between males and females, it's fairly similar. We're just seeing a statistical significance among the females. So it's kind of like this slide here among the split by race ethnicity. We are still seeing like differences across the Japanese Americans, right? It's just not significant. Because the trend in the whites was much more evident trend, and that's the similar pattern we saw in males and females. Much more evident trend in the females and a smaller trend in the males. So I think that's why it was statistically different.
There's also a request in the chat if they can get the paper to read.
The paper is under review, but
Okay.
as soon as it gets accepted, I'll send it over to you with the link.
Okay, so soon, hopefully.
Hopefully, it's under review now.
Yeah. Any other questions or a hand raised? I don't see anything now, so if you
Okay,
would
great.
like to add or anything to say before we conclude.
Okay, then I'll move on to the next study.
Yes, please.
Okay, so this study is an epigenome-wide association study of smoking dose, and this is an EWAS. We looked at an EWAS of smoking dose as measured by total nicotine equivalents. And we all know that smoking is an established risk factor for lung cancer. And one of the big motivations for studying the epigenetics of smoking dose is our previous observation that smoking history does not fully account for disparities in lung cancer risk. These are findings from our work in the multi-ethnic cohort study that evaluated the risk of lung cancer by race and ethnicity and number of cigarettes per day. Here we have the incidence of lung cancer across our 5 ethnic groups among those who smoked 10 cigarettes per day on the left and 35 cigarettes per day on the right. This analysis found similar racial and ethnic patterns in the rate of lung cancer across these 2 groups. In both cases, Native Hawaiians and African Americans had higher rates of lung cancer, these 2 lines, in both those who smoked 10 cigarettes per day on the left and 35 cigarettes per day on the right, while Japanese Americans had lower rates. This racial and ethnic variation in smoking-related lung cancer risk may be in part due to racial and ethnic differences in the uptake of nicotine from each cigarette. The sum of nicotine and its metabolic byproducts can be quantified as something called total nicotine equivalents, otherwise known as TNE. So TNE includes nicotine and all these other byproducts through the metabolism of it. Total nicotine equivalence accounts for 85% of nicotine uptake and serves as a very excellent measure of internal smoking dose. Internal smoking dose, as measured by total nicotine equivalence, also appears to vary by race and ethnicity. In the multi-ethnic cohort study, urinary TNE levels per cigarette were higher among African Americans and lower among Japanese Americans compared to whites. This is consistent with the corresponding higher lung cancer risk for African Americans and lower lung cancer risk for Japanese Americans. Furthermore, racial and ethnic variation in the impact of smoking on lung cancer risk may be explained by differences in DNA methylation. DNA methylation is an epigenetic modification where methyl groups are added to specific sites across the genome, which can then alter the expression of those genes. Smoking status has been observed to be associated with differential DNA methylation for over 2,600 CpG sites across 1,400 genes across the genome. Most strongly, the most common CpG modifications are on sites on the genes AHRR, F2RL3, and GPR15. However, smoking status does not account for the variation in internal smoking dose that results from differences in nicotine uptake and metabolism across individuals. Because total nicotine equivalence is a more reliable measure of nicotine uptake, understanding the association between epigenetics and smoking dose as measured by TNE may provide more insights into the racial and ethnic-specific mechanisms of lung cancer risk. However, there's still limited information on this relationship, especially among racial and ethnic minority groups. Therefore, our objective for this study was to further elucidate the impact of internal smoking dose as measured by total nicotine equivalents on DNA methylation in multi-ethnic populations. And again, specifically because prior studies were mainly done in white populations, our second goal was to delineate ethnic-specific and trans-ethnic variations in these smoking-related epigenetic modifications. Again, we performed the study using data from the multi-ethnic cohort study, but this was one of 3 of the prospective cohorts that we used for this study. Our discovery cohort was a multi-ethnic cohort study where we used data from a subset of about 2,000 participants in the MEC who were current smokers and had DNA methylation data and urinary total nicotine equivalence data. In this sample, we had about 300 to 500 individuals from each of the 5 racial and ethnic groups, ranging from about 311 Native Hawaiians to 522 Japanese Americans. We pursued validation. Hearing an echo. Pursued validation in 2 external prospective cohorts. The first was the Singapore Chinese Health Study, or the SCHS, which is a prospective cohort of about 63,000 Chinese individuals who were aged 47 to 74 from Singapore. The second validation cohort was the Southern Community Cohort Study, or SCCS, which is a prospective cohort of about 86,000 African American and white individuals aged 40 to 79 from the southeastern region of the United States. The SCCS is the special cohort because of all prospective cohorts in the US, it has the highest proportion of African Americans. About 2/3 of the cohort is African American. For both validation cohorts, we used data from a nested case control study of lung cancer among all current smokers. In total, we had about 734 individuals in our validation populations. In our modeling for epigenome-wide association study, our exposure of interest was smoking dose as measured by total nicotine equivalents measured in the urine. This was quantified using liquid chromatography and mass spec. The outcome was DNA methylation, which was measured in the blood using the EPIC version 1 array, which measures methylation at 850,000 CpG sites across the genome. After pre-processing the DNA methylation data, DNA methylation was quantified using a beta value ranging from 0 to 1, with larger values indicating more methylation. To perform the EWAS, we ran a series of linear regressions that adjusted for age, sex, principal components for genetic ancestry, DNA methylation predicted cell types. In the discovery phase, we ran EWASs separately within each of our 5 racial and ethnic groups, and then meta-analyze the results to get one single estimate per CpG site. For the sites that were significant in the discovery phase, we then pursued validation in the Singapore study and the Southern Community Cohort study. Models were run within each of the racial and ethnic groups and stratified by case status. Again, remember that this is a case control study of lung cancer. So in total, we had 6 groups where, again, we meta-analyzed the results to get a single estimate per CpG site. This slide is showing a Manhattan plot that shows the results from the discovery EWAS of total nicotine equivalents in the multi-ethnic cohort study. I'm sure some of you are familiar with Manhattan plots, but each dot here represents a negative log 10 p-value for the association between total nicotine equivalents and DNA methylation at each CpG site across the genome, with higher dots indicating more significant findings. Using a genome-wide significance threshold of 9 × 10⁻⁸, as shown by this horizontal red line, we observed that TNE was associated with differential methylation at 408 distinct CpG sites. The red dots represent a positive association, meaning that higher levels of TNE was associated with increased methylation, while the blue dots represent an inverse association. As you see from this figure, most of the significant sites were negative associations, with the strongest findings observed for known smoking-related sites on AHRR, F2RL3, chromosome 2, and RARA. These are all sites that were found in past EWASs looking at smoking status, so comparing current smokers to never smokers. When evaluating the risk or the results across race and ethnicity, we found that total nicotine equivalence was associated with DNA methylation at 4 sites in African Americans, 3 sites in Native Hawaiians, 21 sites in whites, 38 sites in Japanese Americans, and 37 sites in Latinos. Although there is some variation in the number of significant sites and the level of significance, we generally found that CPG sites in AHRR are among the top hits in all of the racial and ethnic groups, is indicated here. I've labeled here. We can also visualize the results using something called a circular genomics plot, where each ring provides a new layer of information. Here, the most outer ring represents the chromosome. The second ring represents the position of that CPG site on that chromosome. And the third ring shows the direction and of the association, as well as the novelty of that site. Here, circles represent a positive association, triangles represent a negative or an inverse association, and those sites represented by orange indicate a novel site that has not been found in previous studies. In our analysis, we found 45 novel sites. So if you can count, I know it's small, but there are 45 of these orange sites, which are annotated here in the center. The top novel sites here were on chromosome 17, the gene SLC28A1, CXXC5, MIR383, and SPTBN1. Now, all of these genes have been previously associated with smoking and cancer in the literature. But here we're finding that novel CPG sites that are differentially methylated and associated with smoking dose as measured by total nicotine equivalence. Taking it one step further, we can then add in another ring to represent the hits that are replicated in our 2 validation cohorts. Of the 408 significant findings that are represented here by this third ring in the multi-ethnic cohort, 51 of them were replicated in the Singapore study and the Southern Community Cohort study. These replicated hits are now annotated in the middle here. Many of the validated hits were on known smoking-related genes such as F2RL3, AHRR, and RARA. We also found that one of our novel hits in the discovery phase was replicated in our validation cohorts. This was this CPG site in the gene PRSS23. And this gene has also been previously associated with smoking in the past literature. Next, we looked at the variation in the effect of total nicotine equivalence and DNA methylation across race and ethnicity. We found 2 CPG sites that showed racial and ethnic heterogeneity in the multi-ethnic cohort, the first being this site on CYTH1. And CYTH1 encodes for a cytohesin that mediates the regulation of protein sorting and membrane trafficking. Looking at this forest plots, which shows the effect of total nicotine equivalence on methylation at this site across each of these groups, we see that there is a significant positive association only among the African American population in the multi-ethnic cohort study. This was then replicated in the African American controls in the Southern Community Cohort study, suggesting that this CPG site could be impacted by smoking dose only among African Americans. Another potential site was this CPG site on the gene MYO1G. This forest plot here shows that there is a stronger association between T&E and DNA methylation at this site for the Latinos in the multi-ethnic cohort study. However, because of a lack of Hispanic or Latino participants in our validation cohorts, we could not validate this racial and ethnic specific strength of this association in our validation cohorts. In this multi-ethnic epigenome-wide association study of total nicotine equivalence, we were able to demonstrate the trans-ethnic effects of internal smoking dose on 408 CBG sites, including many known smoking-related sites. We further identified 45 novel sites not previously reported, indicating that smoking dose may provide additional information beyond known smoking measures such as smoking status or other biomarkers such as cotinine. We also observed potential heterogeneous effects by race and ethnicity, suggesting that smoking may impact epigenetic modification differently across race and ethnicity. And finally, I hope that in my research today, that I presented today, I was able to indicate how omics-based investigations in diverse populations can play a critical role in our understanding of how omics may contribute to cancer health disparities. Further research in this field can help to elucidate ethnic-specific biological pathways, improve the identification of high-risk individuals, and reduce the burden of cancer for racial and ethnic minorities. The research that I shared today was a big undertaking across multiple institutions, so I'd like to take this time to thank our study team across all these institutions, the funders of our study from the NIH and the American Institute for Cancer Research, and of course to the participants of our 3 cohorts. And thank you for your attention, and now I welcome any questions.
Thank you, Dr. Brian, for the insightful presentation. We will now open the floor again for questions from our audience. If anyone have a question, please use the raise hand feature or type your question into the Q&A box. I will address as many questions as possible within our time. Let me check the inbox. Yeah, I don't see any question from my side.
Excuse me, I have a question for Dr. Brian.
Yes.
Usually in the first study and the second one, you included participants from African American origin. So my question, why you didn't make collaboration with African country and recruit Africans from Africa continent?
Yeah, that's a great question. We would love to include data from those countries. The people who started the study, I think when they apply for the grant, they just focus on these 3 populations initially. But I think now that we're seeing some hits that may be reflective of African-specific hits or hits mechanisms associated with individuals with African ancestry, I think a definite next step would be to look at this data in other sources from populations in Africa. So I think that's a great suggestion. We would love to do something like that if that data is available.
Thank you.
Yeah, so I don't know, at your university, does anyone do epigenetics research?
If any of the audience know if their university or institution can interested or can provide this kind of research, it would be a great good chance to collaborate.
Yeah, definitely. It's a great next step, and we'd love to collaborate and work with other people, because validation is always very important in any of these kind of omics researches.
Especially in African with diverse background, genetically.
Absolutely.
Yes.
I don't see anyone else. Yeah, there's a raised hand. Mariam, you can go.
Hello, everyone. My name is Mariam Abdrashid from Kenya, place called Isiolo County. I wish I could collaborate with Brian. I wish I could engage
wonderful.
him physically.
Okay, great.
Thank you. Today I learned a lot. Anyway, I'm a student. I'm also a social worker. So I wish I could collaborate with you one day, one time. I hope so.
Sure,
Thank you.
Yeah, happy. My email's here if you want to reach out.
Anyone else? There is lots of well done on the chat.
Oh, thank you. I can't see the chat, so
Yeah.
thank you for that.
So if there is no other questions or comments, thank you again, Dr. Brian, for answering the questions and for your excellent presentation. It was a pleasure to have you with us, of course. Thank you all for attending. We hope you found it informative and enjoyable, and have a great day.
Great. Thank you so much. Thank you again for inviting me.
Okay, you're welcome.
Thank you, Dr. Brian.
Thank you. Have a good weekend.
And how can someone join you guys? Like,
Mariam?
Brian. I'm asking Brian if a person
Yes.
from Kenya can join your team, maybe there. So I could like to join you guys, but I know there is a process. Now,
yes, why don't you email me? We can set up a separate time to talk.
Pandal again?
Why don't you send me an email? Did you just get my email on the slides?
Like if I could, I want to join your university, I can see. So I know there is a process.
Mariam, do you hear?
Maybe you can give me.
Can you hear Dr. Brian well?
No.
Yeah, we will provide you with Dr. Brian's email so you can communicate with him.
Okay, thank you.
So here's my email on the screen.
Here is the email. You can see it on the slide, Mariam. Yes, it's also in the chat.
Yeah, please send me an email. We can talk further.
Okay. Thank you again, Doctor.
Thank you.
Thank you. So question in the chat from Oscar. Is it defined in the paper? Yeah, it's defined in the paper, but the paper is still under review. But as soon as it's accepted, I'll definitely share it with your group.
Yes, thank you for that. Okay, thank you all for attending and have a great day.
Okay, thank you. Have a great weekend.